the genetic basis for characters is not the only factor that can influence your physical characteristics or the physical characteristics of any organism. There is an environmental factor as well. You may well be aware that the average height of people in the United States today is greater than it has been historically. And it's not because there are new genes that make people taller, or we've had an immigration event with lots of very tall people. It has to do with other things like the kind of food we eat, how much exercise we get, things that we know about health and nutrition that enable us to reach greater heights. So a departure from Mendelian genetics may come up when there is an environmental aspect to the phenotype as well as a genetic basis for the phenotype. So the range that we see is typically greatest when we have polygenic characters. So many genes, like for skin tone, interacting with each other. You probably know that your skin tone has an environmental basis as well as a genetic basis. If you go out and sit on the beach, you might fry your skin, or you might get a nice bronze tan, and that is an environmental influence. How the degree to which you may tan or burn may have a genetic basis, but the actual tone of your skin on any given day has that environmental impact. So traits that depend on multiple genes combined with multiple environmental influences are called multifactorial, many factors, in addition to many genes. So polygenic comes to us from Greek, many genes. Multifactorial comes to us from Latin, meaning many factors. So a very simple example are hydrangeas, the flowers of hydrangeas. These are very, very common around here. Very beautiful flowers. You've probably seen them around, and you may have noticed that sometimes they're pink and sometimes they're blue. And they are pink and blue just in response to the soil pH. So if the pH is very low, very acidic, they're going to be more pinkish. And if the pH is high or basic, they're going to be more blue. So that is an environmental factor that affects the flower color rather than a genetic basis for it. Although the fact that they change, that there's this pH-dependent factor does come from the genetics of the pigments. The fact that they're influenced by pH is also genetic, because other flowers don't have that genetic basis. For a more relevant to you example, the number one cause of death in the United States is heart disease. It's close to 25%. About 23% of deaths in the United States are attributed to some type of heart disease. That said, it seems like, well, that should be a target for medical science to go after. And as it turns out, we do know a lot about heart disease, but it's still a very complicated disease to identify and treat because it is multifactorial. There is a genetic component to it. You may have, there are a number of things that contribute to heart disease: blood pressure, your body mass, your BMI, how your body metabolizes cholesterol. So there's that genetic basis, but then there's also an environmental component. If you have a very low cholesterol diet, if you choose not to smoke cigarettes, or use tobacco, if you choose to be physically active, all of those are positive factors that are going to reduce your risk of developing heart disease. So that's what we mean by it being a multifactorial disease, and it's not simple. You've probably heard of, so and so. My grandma smoked a pack of cigarettes every day until she was 99 years old, and then she got hit by a bus. Something like that, where she beat the odds for dying of heart disease. But again, that's the nature of multifactorial diseases, which isn't to say that everyone should start smoking and start eating a high-fat diet, because medical science will save you, or maybe you have the genes to not get heart disease. But if you want to reduce your risk of developing heart disease, we do know of some environmental components that can help to make the genetic components of heart disease, things like cholesterol metabolism, high blood pressure, less have a lesser impact. Okay, so learning objective 9 is looking at another type of genetic disease, hemophilia. So if a mother is a carrier, what is a carrier? We'll define that, for hemophilia, and her husband has hemophilia, what are the chances that their daughter would have hemophilia? So hemophilia is a little bit different. Again, we do see Mendelian rules being applied. However, they work a little bit differently because hemophilia is an X-linked gene. The gene for hemophilia, that allele, is on the X chromosome. The X chromosome, everybody's got an X chromosome, males and females. Females have 2 X chromosomes. Males have 1 X chromosome and 1 Y chromosome. So what that means is if you are male and you only have 1 X chromosome, any genes that are present on that X chromosome are going to be expressed. You are going to have, if there is a disease caused by a recessive allele that's on the X chromosome, and you are male, you only have 1 copy of that gene, and so you don't have a second copy of, if you have the dominant, you don't have a dominant allele to mask the effect. So X-linked genes that are recessive follow very specific patterns of inheritance. So if a recessive X-linked trait is going to be expressed, a female has to have 2 copies of that gene, so no dominant allele to mask it. But a male only needs 1, and we kind of have this word hemizygous, which means half the chromosomes, or you just have that 1 X chromosome, which is enough to make you express that disease. So X-linked recessive disorders very much more common in males than in females. And some examples, well, before we get to the examples, let's see Punnett squares to reflect on how that works. Okay, so in humans, not all organisms, not all animals, but in humans and many, many other organisms, if you are XY, you are male, and if you are XX, you are female. And you inherit an X chromosome from your mom, everyone does, and then dad can either pass along his Y chromosome or his X chromosome. Okay, so if this gene we're looking at is called N, again, we're going to use these superscripts to indicate dominant and recessive alleles. Okay, so here's mom, who's got a dominant N gene for a disease, and dad, who has this disease. He's got the recessive allele. So when he produces his gametes, he can either pass on his normal X, his mutated, his diseased version of that allele, or his Y chromosome. Mom can only pass on the normal type of this allele because she's homozygous for this X capital N. So what happens in the progeny? Well, all of the males will be normal. All of the females will have 1 copy of that that allele, and one copy of the normal allele from mom. So that these are what we call carriers. They don't express the disease, but they have the genetic potential to pass it on to their children. So let's say that one of these daughters marries an unaffected man. What's going to happen? What's going to be the fate of their children? Well, as she is a carrier, she may have, there's no chance that her daughters will have this disease, this genetic condition, because they're going to have two copies of the X chromosome, and dad is always going to pass on the normal version. But for the daughters, half the daughters are going to be carriers and half are not going to be carriers. And for the males, half are going to have the disease statistically, and half will not have the disease, depending on what mom passes on. Okay, if mom is a carrier and dad has the disease, what is the likelihood of the daughters and sons having the disease? This is the only case where a daughter can have this condition, is if she gets two recessive copies of this N allele. The daughter that is not affected is still going to be a carrier. The son who does not have the disease is not going to be a carrier, not going to be affected, not going to have the disease, but half of the sons will have that disease, statistically speaking. So a little bit different ratios from what we saw with the flower color allele in peas. So some disorders are relatively common that are on the X chromosomes in humans. So red-green color blindness, there are many different types of color blindness, but the most common type is an X-linked allele, which is why most of the colorblind, red-green colorblind people you meet are going to be men. Duchenne muscular dystrophy is another, and then hemophilia is another, the one that's most germane to our conversation, because that's what the learning objective is all about. So hemophilia is an X-linked recessive disease. Okay, so hemophilia, it means love for blood. Hemo is blood. Philia is love of. So what that means is a clotting factor is defective. So your blood doesn't clot properly, which means any wound is going to bleed for a long time, and which, if your blood doesn't clot, that can expose you to some very dangerous situations. So, you can't be a huge risk taker if you're a hemophiliac. And Queen Victoria of England, she was not a hemophiliac, but she was a carrier for this gene, which had some very interesting repercussions that I'm going to tell you about at the end of this chapter. So back to the original question, if mother is a carrier for hemophilia and her husband has the disease, then what are the chances their daughter would have hemophilia? Okay, so again, we can map out on a Punnett square the gametes, the potential gametes, because mom's a carrier, so she's got one X chromosome that is normal, not hemophiliac, one chromosome that has the hemophilia gene allele on it. Dad has the disease. Somehow he survived to get married and produce children. So what does it look like? Well, half the sons are going to be normal. Half the sons we expect to have hemophilia. What about the daughters? Half of them will be carriers. They're definitely going to have the allele, at least one copy. And then half of the daughters are going to be hemophiliacs. So remember, X with a capital H is the normal allele. X with a lowercase h is the diseased allele. So for a female to actually express or to have hemophilia, she needs to have 2 copies of that X little h. So half of the daughters are going to have hemophilia, and the other half are going to be carriers. Learning Objective 10. If a father who is heterozygous for Huntington's disease has children with a normal female, what are the chances their daughter will have Huntington's disease? Huntington's disease is another genetic disease, but it doesn't get passed along in the same way as we've seen with other of these diseases we've talked about. Something that is important to note is that in Mendel's experiments, his ratios that he observed were for genes and alleles that had no effect on the fitness or how likely it was that the pea plants were going to survive. And a dominant allele is not subduing a recessive allele. It may be able to mask a recessive allele, but at the end of it, the alleles are just variations in the DNA, in the nucleotide sequence. By the same token, dominant alleles aren't necessarily more common than recessive alleles. So polydactyly, or having extra digits, fingers or toes, is a dominant allele. However, it is a rare dominant allele. Only about 1/4% of children are born with extra fingers or toes. Typically, they are going to be removed shortly after birth. But yeah, it is a thing that happens, and it happens to be relatively rare. So there are many different degrees to which somebody can express polydactyly. This is a grown man who's got 6 fingers, apparently functional on each hand, but it might just be a little bit of a stub of a finger or something like that. But the recessive allele is much, much, much more prevalent than the dominant allele. So we don't always see like this 3-to-1 ratio of the dominant phenotype to the recessive. And that is a good thing because there are some dominantly inherited genetic diseases. Huntington's disease is such a disease. It is a neurological disorder which typically is only expressed after a patient has reached at least their 30s. Usually you don't start seeing symptoms until a patient is in their 30s. So they might not know that they have it, get married, have children, and pass on this gene before they even are aware that it's a possibility. But it's a very damaging neurological disorder. All parts of the nervous system will degrade over time. So onset is typically later in life. It's caused by a dominant allele. One of the most famous patients who's had Huntington's disease was not Huntington himself. I think Huntington was the doctor who described it. But this fellow here, Woody Guthrie, who was a very prolific songwriter and musician. He wrote the song "This Land Is Your Land," among many others. But he had Huntington's disease. So, if a father who is heterozygous for Huntington's disease, and will express it, crosses with a female who does not have it, what are the chances their children will have Huntington's disease? Again, we can use a Punnett square. And, oops, that should be a lowercase h. The answer is actually 50%. And we can see that Woody Guthrie has a son named Arlo, who's also a musician, who, fortunately for Arlo, does not have the disease. Arlo has, I think, 7 siblings, of which about half of them have succumbed to Huntington's disease. Again, I'm sorry, that's a boo-boo on my part. That should be a little h, little h. he should be all big H.